Okay, derivatives of polynomial functions. They've given us quite a few functions. What this is the first one is if the function is k, which is a constant term. So if it is just one term, no variables involved, the derivative, remember f prime deals with the derivative. We just talked about that with our first principle of derivatives. The derivative of that function will just be 0. That's it. If our function has a variable to an exponent, this is called your power rule. The derivative of this function will be taking the power, putting it down in front. So our n, you now multiply it. It's the coefficient in front of the variable. And whatever the exponent was before, for instance, if it was the number 5, so this was x to the 5th, 5 came down here. And our new exponent is 5 minus 1, which is 4. So we then had 5x to the power of 4. We'll do an example. That was just something very quick. Our next rule here is the constant multiple rule. And what this is saying is if you have some function with a constant term multiplied by the function, the derivative of that function is that constant term times the derivative of that part of the function, which takes us back to these rules. And finally, your sum rule is if you have two functions added to each other, the derivative of it is just the derivative of the first function plus the derivative of the second function. And the difference rule, same idea, two functions subtracted by each other. The derivative of that is the derivative of the first subtracted by the derivative of the second. A lot of words, no numbers. Let's attach some numbers to this. So, we'll go right into example, I don't know, 3, I guess. We'll just make a few up along the way, just so it makes sense. Okay. Power function. Well, I guess the first one's important. Okay. For instance, let's say we have these. They've given us g at x is equal to root x. F at x is equal to good. We'll do x cubed. H at x is equal to 1 over x. And what? F, G, H. We'll say E at x. I know you don't see that often. Is equal to 5. Okay. I'm going to try to encompass a couple of these rules real quickly. We'll actually start with E at x. So let's say the very first question asked us for E prime x. In other words, the derivative of E x. Well, because this is just a constant term, what is the derivative of this constant term going to be equal to? 0. That's exactly what that rule states. Okay? It is equal to just 0. Okay, so we have that one. Let's say B gives us find the derivative of, or find f prime x. Okay, well we know f at x is equal to x cubed. According to our product rule, or rule of exponents, we take our exponent term, bring it down in front, and we subtract it by 1 to find out its derivative. So f prime x becomes the coefficient, then becomes the number 3. Our variable is x. And what is 3 subtract 1? 2. So bright, Chris. F prime x is equal to 3x squared. Okay. So that's using our product rule. Those are very straightforward examples. These two next two get a little harder. Question C maybe asks us for g at x, or g prime x they ask us. Well, if you remember, g at x was the root of x. Well, I can turn this into an exponent. Anyone know what this root exponent is? Half. That's right. So this could also be written as x to the power of 1/2. Well, when I'm finding g prime x, our product rule comes into play again. Our half now becomes the coefficient of x. And our exponent, I meant to write that in black. Our exponent then becomes, and I'll write it up here just so we have an idea, 1/2 subtract 1. Well, as a fraction, that's 1/2 minus 2 over 2, which gives us negative 1/2. So in other words, our exponent here becomes negative 1/2. So g prime x is actually 1/2 x to the power of negative 1/2. Okay? Negative 1/2. Say they asked us to only write it as positive exponents. How can I write negative or x to the power of negative 1/2? 1 over well, root x essentially. Because this is a root and it's a negative. If we need to make this exponent positive, we still have our coefficient here. If we were to make it positive, it technically becomes 1 over x to the half. And we just discussed how x to the half is the same as a root. So we could write this as 1/2 multiplied by, still multiplied by, root x. And as one final term, it becomes 1 over 2 root x. Now, I don't know if you guys remember this, but using first principles, we went through this exact example with, I think it was the letter T. We did this using first principles. It just took a heck of a lot longer to get to this answer here. Okay? If you know all of these rules real quickly, you can jump right to this from here. Okay? Either is fine. This is also an acceptable answer. This is an acceptable answer. Okay? And finally, what's our last example? Is it h? H prime, yeah. Okay, say they finally ask us for, D says, find h prime of x. Well, h at x was equal to 1 over x. Probably should have done this expression first. We can make this an exponent. Let's make this negative, okay, in this case. So we then have x to the power of negative 1. That is still the same as h at x. And if I have to find h prime x, or the derivative of this, that now becomes the coefficient. So we have negative 1 as our coefficient in front of our variable. And we have negative 1 subtract 1 gives us a negative 2. So our exponent is now negative 2. And say they only want it written as positive exponents. Well, this becomes negative 1 over x squared as your derivative. Okay? So that was your product rule and your constant rule all in